Welcome back to Physics with Miyoshi. This time we're going to talk about Newton's third law, which says when one body, or something like this, when one body exerts a force on a second body, the second body exerts an equal and opposite force on the first body. It's also called the action-reaction law many times. And so it's very simple. You just have to remember that if I have two objects, we're going to have one, maybe an astronaut or something. They like to use, oftentimes people like to use astronauts in space exerting a force on something else, because that way there's seemingly no other forces acting on it. We have the astronaut acting on some body in space, pushing it. That body has a big mass of 11,000 kilograms, and our astronaut has a mass of 92 kilograms. And if the astronaut pushes on the big object, an asteroid or spaceship or something, with a force of 36 newtons, in this case we'll call it a push from 1 to 2, in other words from the astronaut to our other body, then that body also exerts a force on the astronaut of the same value. So the push of 2 to 1, that just means, it just means the body acting on the astronaut of 36 newtons also. So here's my action force, and here's my reaction force going the opposite direction with the same magnitude. So we can look at this a couple different ways, but mainly I want to show you a quick example, and that is that I'm going to draw a free body diagram and show you that even though the forces are the same, because the masses are so different, the accelerations are going to be different as well. So if I look at the astronaut here, consider him as M1, or her as M1, then the force on the astronaut, we can look at the astronaut here and see that the force there is 36 newtons going to the left. So my acceleration 1, if you will, is sum of all my forces divided by mass 1, and we can remember that's from Newton's second law. I just divide my force, 36 newtons, by my 92 kilograms, which is its mass of the astronaut, and we get 0.39 meters per second squared going to the left. Then if I look at the same thing, I'll do the same thing. I'll do a free body diagram over here with my mass, my asteroid or my spaceship, whatever it happens to be. It's got the same force, but acting in the opposite direction, the force of the astronaut. So my acceleration there is the sum of my forces divided by mass 2, or the mass of my object, and that's going to be 36 newtons divided by, in this case, 11,000 kilograms, and we get 0.0033 meters per second squared. And that is going to go to the right. Now, if you look at these two guys, they're much different in magnitude, and that's to be expected if we think about it. If I push off on the Earth, for instance, if I jump in the air, then I'm exerting a force on the Earth, and that Earth is exerting a force up on me. I'm going to accelerate quite a bit more than the Earth will. And in reality, the Earth does feel an acceleration, just like this mass feels an acceleration away from the astronaut, and that astronaut feels an acceleration away from the body. And those two are proportional to their masses. Actually, the accelerations would be inversely proportional to the masses. At any rate, that's so we get what we expect, and we see an application of Newton's third law. So that is, in its essence, Newton's third law. We see that my masses, or the forces, are going to be equal but in opposite directions, and in this case we also demonstrate that the accelerations, when they would be different based on their masses and those same forces. So thanks for tuning in, and look forward to seeing you back here on Physics with Miyoshi.